Hello and welcome to the NDI Professional Certification course, a series of 6 modules designed to improve your knowledge of NDI technology and support you through more complex system designs and implementation. Before we head into the course, let's take a look at what's coming up over the next 6 modules.
In the previous course, we laid the groundwork for understanding how video, audio and control data flows across an Ethernet network using NDI. We looked at the evolution of AV over IP and explored the differences between NDI and traditional technologies like SDI and introduced NDI's unique strengths: software-defined, scalable and cost-effective. You also learned how discovery and registration works and the role of the OSI model and how to begin building reliable, basic NDI workflows with the right switch configuration and endpoint setup. And we wrapped things up with some real-world scenarios to help you decide when and when not to use NDI. This time, we're going deeper. Throughout this course, you'll explore more advanced elements of NDI operation, what it truly means to be a professional user. We'll take a look at how NDI works across subnets and how protocols like IGMP and PIM are used to manage multicast traffic, and how complex switching configurations affect signal behavior. You'll learn to handle synchronization and configure advanced control settings and integrate NDI into cloud-based workflows. Plus, we'll be digging into NDI tools in more detail and unpack the design principles behind efficient, high-performance NDI systems. By the end of this course, you'll be able to achieve an in-depth understanding of NDI, covering its core principles, technical complexities, and operational nuances, far beyond the general user level. You'll be able to confidently manage and troubleshoot complex NDI infrastructures, including advanced production environments using discovery servers, Genlock, and WAN transport. You'll also be able to design creative, sophisticated NDI solutions that meet high-level production demands, applying strategic thinking to real-world workflow challenges. Let's get started and unlock the full potential of NDI.
In traditional AV systems, connections between devices are straightforward using physical cables like HDMI or SDI. However, in NDI's IP-based ecosystem, video, audio and metadata are transmitted over a network. This shift introduces complexities that require advanced knowledge to manage and optimize. Advanced users must understand that not only the principles behind these workflows, but also how to resolve issues and implement strategies that keep systems running efficiently. For example, in a live production setup where dozens of NDI-enabled cameras and devices are interconnected, network congestion can cause delays and interruptions. An advanced user knows how to identify bottlenecks and apply solutions such as traffic prioritization and multicast configurations. This ability to navigate the complexities of NDI distinguishes advanced users from beginners, empowering them to deliver seamless and professional results every time. NDI discovery allows devices to identify and communicate with each other automatically. Now, when an NDI-enabled transmitter comes online, it announces its presence using MDNS by broadcasting service advertisements on the local subnet. Receivers listen to these advertisements to build a registry of available sources. This passive listening approach reduces the need for manual configuration, as well as accelerate setup in environments where MDNS traffic flows freely. For instance, a production team might deploy a new NDI camera just minutes before going live, and the camera will immediately appear in the list of available sources on NDI receivers, assuming the network supports NDNS properly. However, challenges can arise in more complex network environments. Firewalls might block NDNS traffic on UDP port 5353, or the network might be segmented across multiple subnets that don't support multicast routing. In such cases, devices might not discover each other automatically. And to address these limitations, NDI also supports NDI Discovery Server, a centralized discovery method suitable for large or segmented networks. Instead of MDNS, NDI devices are configured to communicate with a specified discovery server over unicast. Transmitters register themselves with the server, and receivers query it for the list of available sources. This approach then ensures reliable operation across routed networks, data centers, or when tighter network control is required. Advanced users must also be familiar with both discovery methods, verifying subnet configurations, enabling appropriate multicast settings, and using tools like NDI Access Manager to specify preferred discovery servers or manually add remote sources. They're all key to maintaining a robust and scalable NDI environment. NDI has evolved through several major versions, each introducing transport layer improvements to meet real-time video production demands across various network topologies. NDI 1 gave us single TCP, this was the initial implementation of NDI, and it used a single transport control protocol. And while this approach guaranteed reliable delivery, it proved to be less scalable in environments with a large number of NDI devices. TCP's connection-oriented nature and retransmission mechanisms can lead to excessive network overhead, and that makes it less suitable for high-density production workflows where hundreds of streams may coexist simultaneously. NDI 3 gave us UDP with FEC and multicast. Now, NDI 3 significantly evolved by adopting UDP or User Datagram Protocol for video and audio transport alongside FEC or Forward Error Correction to compensate for packet loss. This shift significantly reduced latency and improved real-time performance in typical LAN environments. Importantly, multicast support was introduced, allowing a single NDI stream to be distributed efficiently to multiple receivers without duplicating traffic, which is ideal for large-scale or multi-viewer setups. However, using UDP with FEC has trade-offs because it typically increases overall bandwidth usage compared to TCP, and that's due to the additional error correction data. Furthermore, FEC requires extra processing resources on the receiver side, as packets have got to be reconstructed from redundant information to recover lost data. This overhead can impact performance in scenarios with limited CPU capacity or constrained network links, for example. NDI 4 gave us multipath TCP and was introduced with multipath TCP to allow devices to leverage multiple network interfaces in parallel. Now, this boosted bandwidth and provided redundancy, but its effectiveness could vary depending on the balance and configuration of connected interfaces, for example, mixing 10 gigabit Ethernet and 1 gigabit Ethernet links. So NDI 5 gave us reliable UDP or RUDP. NDI 5 adopted RUDP as the standard transport mechanism, blending UDP's low latency benefits with enhanced reliability. Now, RUDP includes packet sequencing, retransmission, and congestion control to ensure consistent media delivery even under the most challenging network conditions. Deploying NDI in complex environments such as broadcast facilities or large corporate venues or even multi-floor event locations requires precise network design to ensure stability and scalability and predictable performance. Our key foundation is IP address management. Using static IPs, for example, or DHCP reservations, Well, that avoids source name conflicts and discovery issues, especially when dealing with dozens or even hundreds of devices. Segmenting the network using VLANs in larger setups also helps to isolate NDI traffic from unrelated data. And since NDI relies heavily on low latency, high throughput unicast transmission, network switches must be configured with proper buffering and flow control. And while NDI can work on general purpose networks, in professional environments, it's critical to make sure that all devices are connected through non-blocking gigabit or 10 gigabit Ethernet switches. The switch fabric has to be properly dimensioned to handle peak aggregate throughput and make sure that there is a minimal hop count and consistent latency between sources and receivers. Although NDI supports multicast starting from version 3, it is disabled by default. IGMP snooping and querier configurations are only relevant when multicast is explicitly enabled, and that's covered in a dedicated chapter of the course. Advanced users also extensively use tools such as NDI Access Manager to manually configure routing between subnets or set up devices to register with an NDI discovery server. And this all becomes essential in routed or segmented environments where MDNS is not viable. In these scenarios, proactive design decisions like reserving bandwidth per stream or ensuring dedicated switching paths and mapping device flows are critical, because this avoids hidden bottlenecks and allows for seamless operation even under pressure. Ultimately, building a high-performance NDI deployment in a complex environment means treating the network as part of the production chain, applying the same rigor used for video signal paths and ensuring deterministic behavior across all components. NDI Tools is a fundamental software suite for anyone working with NDI. This includes essential utilities that help users get started with NDI, exploring its capabilities and managing more complex infrastructures. While some tools serve as entry points for discovery and testing NDI sources, others are critical in maintaining and controlling large-scale multi-device environments. NDI Studio Manager is a powerful application that's ideal for basic source verification, remote preview, and confidence monitoring. NDI Access Manager is a key tool for configuring how a system interacts with other NDI devices. It's available for Windows and Mac OS, and users can modify the local NDI configuration file via a user-friendly interface. And its main functions include things like managing NDI groups, where users can define, send, and receive groups to separate devices and logically control source visibility. A device will only discover or be visible to each other devices in the same group. So this makes this feature essential for multi-team productions or installations with overlapping workflows. With manual source configuration, it allows manual connection to specific NDI transmitters located on different subnets or across networks where MDNS discovery is impossible. And this ensures reliable access to remote sources. With multicast settings, Access Manager can enable or disable multicast transmission for each device, allowing multicast-aware networks to distribute streams more efficiently. And Discovery Server setup allows configuring NDI Discovery Server as an alternative to MDNS. And this is critical in routed or segmented networks where multicast traffic is restricted or disabled. Access Manager isn't available on Linux. All these settings have got to be applied manually in that case by editing the configuration file as documented on the NDI Docs and Guides website. You can find a link for that below. For advanced users, Access Manager is more than a utility. It's a central component for controlling NDI behavior in structured, high-performance IP production networks. The NDI analysis tool, which we'll be covering in detail later, complements this workflow by offering advanced bandwidth, stream integrity, and system performance diagnostics, which are crucial during setup testing and troubleshooting phases. While the OSI model is a theoretical framework, understanding its key layers really helps advanced users to troubleshoot and design stable NDI-based systems. Now, NDI operates primarily at layer 2, or the data link layer. This is relevant when diagnosing switch level issues or MAC address conflicts, or even when dealing with VLAN segmentation. Whereas layer 3, the network layer, this is where NDI relies on IP addressing for discovery and communication. Problems like duplicate IPs, missing routes, or incorrect subnet masks can prevent devices from seeing each other or streaming correctly. At layer 4, the transport layer, NDI uses different protocols. For example, TCP, Transmission Control Protocol, UDP, User Datagram Protocol, or RUDP, depending on the version and configuration. And understanding how these behave, especially concerning packet loss, retransmission, or congestion, well, that's key in complex environments. A practical example is that if a source is not visible, an advanced user may first check the IP configuration at layer 3, then verify VLAN or switch isolation at layer 2, and finally inspect packets and packet flow using tools like NDI analysis or Wireshark to evaluate transport level issues at layer 4. And by mapping NDI behaviors onto the OSI model, professionals can approach problems methodically, saving time during critical workflows and ensuring consistent system performance. Designing a network infrastructure for NDI involves more than just connecting devices to a switch. It requires choosing the correct hardware and configuring that hardware attentively, applying best practices developed through real-world experience. Network switches used in professional NDI deployments have got to meet specific requirements. They've got to have a non-blocking architecture with sufficient backplane bandwidth to support high throughput, low latency traffic. Gigabit or 10 gigabit or even 25 and 40 gigabit ports, depending on the number of resolution and expected concurrency of NDI streams. They need support for flow control, VLAN configuration, and detailed traffic monitoring. Because managed switches contain increasingly complex processing logic and firmware, it's essential to keep the switch firmware up to date. Vendors often release updates that address performance issues and fix compatibility problems while improving reliability, which is especially important in demanding environments like video production. Modern switches are passive conduits and active computing devices that play a key role in the network's behavior. A few configuration considerations specific to NDI include flow control. Enabling flow control on switch ports allows for better handling of sudden traffic bursts. At the same time, it reduces the risk of buffer overflows and packet drops by letting overloaded devices pause traffic momentarily, which is particularly useful in full duplex streaming environments. QoS, or quality of service, since NDI doesn't interpret or use QoS tags, enabling QoS can introduce unnecessary complexity or misprioritization. It's generally recommended that QoS be disabled for networks dedicated to NDI. Although often promoted for high-performance networking, jumbo frames are not recommended in NDI workflows. Many devices, including embedded cameras and NICs, network interface controllers, may not handle them consistently. Furthermore, if a jumbo frame is lost, the impact on the video quality is actually more severe due to the larger amount of data per packet that's lost. Standard MTU values are typically 1500 bytes, and they offer better interoperability and fault tolerances. Using VLANs to separate NDI traffic from unrelated data, for example, office traffic or internet access, can really help to avoid unnecessary congestion and minimize latency. This is especially beneficial in mixed-use networks or when multiple production teams share the same infrastructure. Mastering NDI in professional environments requires more than knowing how to connect sources and viewers. Advanced users must understand how discovery, protocols, and network infrastructure interact to form a stable and scalable system. In this module, we explored the internal mechanics of NDI discovery with MDNS and Discovery Server, as well as look at the evolution of its transport protocols from TCP through to RUDP, and the network configurations necessary for high-performance deployment. We also examined the role of tools like NDI Access Manager and Studio Monitor, and the importance of switch-level features such as flow control, firmware management, and appropriate bandwidth planning. And these foundations are critical for tackling real-world scenarios, from OB vans to multi-floor installations, and from tightly segmented VLAN topologies to multicast configurations. And in the next modules, we're going to be exploring additional advanced aspects of NDI infrastructure, such as multicast deployment, VLAN configuration and usage, of course, as well as techniques for debugging packet loss in NDI networks. Keep building on this foundation to unlock NDI's full potential in complex mission-critical environments, and I look forward to seeing you in the next module.